I am Bursa. I am a World Heritage Site from the depths of history. I am a depository of civilizations on the foothills of Mount Uludağ. I am the ancient capital of the Ottoman Empire and its enduring spirit. I am Bursa. I am the prayers and calligraphy of the Ulu Mosque. I am the tiles and ceramics that give the Green Mosque its name. I am the houses of worship in Iznik, once home to Romans, Byzantines, Seljuks, and Ottomans. I am the Muradiya Mosque complex, where life and death, dreams and reality, poignance and joy are contemplated. I am a boundless land of legends, the living cultural heritage of Cumalikusik, the sun setting on Gölyaza Lake. I am nature's gift to humanity. I am the color green in all its shades. I, a centuries-old sycamore, tones of blue and green, sun and lake, am Bursa. I am the eternal beauty of the Longos forest. I am the rushing waters of the Sai Tabat and Suuchtu Falls. I am a city of flavors, where history meets gastronomy. I am crispy jontik from a wood-fired oven. I am the finest olives and olive oil. I am the birthplace of Bursa kebab. I am köfte with pide and inegöl köfte, that is, a paradise of Turkish-style meatballs. I delight palates with sensational flavors, like soft tahini pide and candied chestnuts. I am a land of fresh fruit and nature's bounty. I am paragliding between sky and forest. I am the center for adrenaline and nature sports. I am the timeless shadow puppets, karagas and hajavats. I am handicrafts at Erganda Bridge, a steel knife forged in fire, a smooth silk shawl from Oguzhan, a handcrafted Iznik tile. I am the last stop before Europe on the Silk Road, the covered bazaar. I am so much more than a city. I am Bursa.
Dear participants and dear guests, welcome to the third and final day of 13th International Electrical, Electronics and Biomedical Engineering Conference, ELECO 2021. We regret that we are slowly coming to the end of our conference, and we are happy that we had the chance to listen to many scientific studies and valuable invited speakers. There is one distinguished invited speaker in today's live broadcast program. With your permission, I would like to invite him. Now, we invite our esteemed Professor Dr. Mr. Ismail from Wayne State University, who's founder of the Ohio State University's Analog VLSI Lab, one of the foremost research entities in the field of nanoelectronics, analog, mixed signal, and RF integrated circuits, to make a presentation on recent advances in wireless charging, which is 7th invited talk in ELECO 2021. And we also invite season chair, dear Professor Oguzhan Cicekoglu.
Okay, thank you very much. Good afternoon, good morning, and good evening to everyone, depending from which location in the world you are connected at the moment. So welcome to the invited talk session of ELECO 2021, which is organized as a virtual conference this year. I am Oguzhan Cicekoglu from Boğaziçi University. Ladies and gentlemen, it's a big honor for me to introduce Professor Mohammed ISMAIL. Since he is well known to electronics as well as circuits and systems scientific community, I will keep this introduction as short as possible. Mohammed ISMAIL has spent over 30 years in academia and industry, having worked in the United States, Canada, Sweden, Egypt, and most recently at Khalifa University in the United Arab Emirates. Professor Ismail is the founding director of Ohio State University's Analog VLSI Lab, one of the foremost research entities in the field of analog and RF integrated circuits. He was a researcher at the Swedish Royal Institute of Technology, KTH, and created the Ramses Radio and Mixed Signal Integrated Systems Research Group. He has served the Institute of Electrical and Electronics Engineers in many editorial and administrative capacities and has co-founded several startup companies in semiconductor and IC design services. Professor Mohammed ISMAIL is editor-in-chief of Analog Integrated Circuits and Signal Processing Journal, and using this opportunity, I wish to thank him again for his invited talks in previous ELECOs and by allowing us to produce a special issue each time. Professor Ismail is currently with Wayne State University, Detroit, Michigan. The title of today's presentation of Professor Ismail is Recent Advances in Wireless Charging. Let us listen to this interesting talk now. Professor Ismail.
And I would like to start by thanking the committee of the ELECO 2021 for inviting me to be with you this afternoon and share some of the exciting work in the area of wireless charging. And after I saw the introduction of Bursa, I can't wait to come back to Bursa, the beautiful place, and meet all the friends in the ELECO society. So, okay, so as Professor Oguzhan said, I'm now in Detroit. I'm the chair of the Department of Electrical Engineering at Wayne State University. And the university is old. We just celebrated the 150 years anniversary 2 years ago. So it was founded in 1868, and we have about 28,000 students from every state in the US. And we have a lot of programs, and it's one of the three major universities in Michigan. We have University of Michigan, and we have also Michigan State and Wayne State, where I am. We are located in downtown Detroit, and actually our location is very unique because we are so close to most of the automotive companies. As you know, Detroit is considered to be the automotive capital of the world. We have 375 automotive R&D centers. Out of them, we have 125 that are foreign headquarters. BMW, Kia, Toyota, Nissan, Mercedes-Benz. And 63 of those top 100 automotive suppliers are headquartered in Michigan. And we have also 12 auto assembly plants. So we have a lot of opportunities. Our students are very lucky to be close to those companies. They get, and the city is growing so fast with the introduction of electric vehicles and also the autonomous vehicles as well. There is a lot of startups in the field of mobility and autonomous cars and EV. So we are very happy to see this big emphasis on automotive these days. The city of Detroit, of course, is located in the state of Michigan. It's the capital of the state of Michigan, and it's located right on the border to Canada. This picture actually is taken from the Canadian side. We have a river that separates Detroit from the Canadian side. And the city of Windsor in Canada is just across the river. So the ECE department is one of the largest departments in the College of Engineering. We have about 300 undergrad and 200 masters and 60 PhDs and 24 faculty members, and we have 4 IEEE fellows, and we have a lot of research funding from industry and also NSF and other places. This is actually our faculty. We cover all different areas of electrical engineering. And inside the department, we founded the WinCAS Research Center, which actually focuses on integrated circuits and systems. And this center actually is directed by myself, and we have 3 faculty members and about 10 PhD students. And we actually look at different research areas in that center, including machine learning, artificial intelligence, IoT, mixed signal, RF and millimeter wave. There is a lot of stuff, and there is a lot of emphasis on research directed to the automotive industry. So we do a lot of chipsets for V2V, V2X chipsets, LiDAR, infotainment, and also everything that it has to do with and as you know, there is a problem right now in the industry. There is a lot of chip shortage, and hopefully the situation will improve over the next few months or maybe next year. We have a lot of resources in the center that will allow us to do sophisticated experiments. And some of the stuff that we have done recently includes the chipsets for Wi-Fi, for biomedical engineering applications, like the one here, for example, self-powered biomedical processor with on-chip wireless communication. That chipset actually was the first to detect the onset of a heart attack before it happens. So just a very quick introduction of this chipset. We have an energy harvest. It's a self-powered, so it basically harvests the energy of the thermal human body and convert it to voltage. And that voltage basically will power up the rest of the chipset, including the machine learning part, the digital part, including the analog to digital converter. And of course, you sense the ECG signal, and then you convert it to digital, and then you do the machine learning, and then you transmit the result to a remote point of care. So the most important aspect of this is that it's self-powered, and it has to do also with the topic of today, which is wireless charging. So how can we actually, for all the IoT devices, how can we make sure that these devices don't use battery, and they can basically be able to harvest RF energy in this case. So the outline of this talk is that we are going to speak about, introduce the so-called wireless power transfer, and the history of wireless power transfer, the types of wireless power transfer and applications, and also talk about microwave wireless power transfer and the applications, including at the end of the presentation, I'm going to present a project that we have been working on for the last year or so, allowing the charging of any device in a way that's similar to Wi-Fi. Like, the Wi-Fi, you can basically move any place in a room or in a hotspot, and you'll be able to connect to the internet. In this case, you will be able to put the device anywhere in a room, in a smart home, for example, and it will be able to receive an energy that would allow it to charge itself. So this is we have a patent pending on this technology that I'm going to discuss. In fact, this is the first time I'm talking about it in a public situation here. So wireless power transfer is just you transfer power without wires. So it's very convenient, it's cost effective, and it's also environmentally friendly because it doesn't require any battery or any. The history of course goes back to a long time ago, and it was Nikola Tesla who actually advocated the wireless power transfer technology, and he transmitted electric power without using wires. He was the first one to do that, and in fact, in the slide, you can see the first paper that came up in 1893, a long time ago, by Tesla himself. And he conducted experiment using inductive coupling and was able to light up a phosphorescent bulb using this technology. Okay, so what are the different types of wireless charging? You have near field, if the devices are so close to each other, and you have a far field. The far field is basically RF, and the near field uses inductive or capacitive coupling or magnetic resonance, and the far field basically uses RF radiation and harvesting. So the inductive coupling basically is very simple. You have a voltage and then a transmitting circuit that goes to a coil, the transmit coil, that's coupled to a receive coil, and the reverse circuitry, you have a receiver circuit and a load here, basically. So you have a primary and secondary coils, and you have energy transfers due to mutual coupling. And it's based on magnetic induction, and the main advantage here is very highly efficient, over 90% the efficiency. And of course, the two coils have to be like perfectly aligned. And if you have some kind of misalignment here, then you would lose some efficiency, of course. But it's basically meant for very short range, single receiver only, so it can only cover, serving one receiver, not several receivers at the same time.
Sorry, dear Professor Ismail, if you want to share some videos or some presentations, you are welcome to do it.
Yeah, in fact, I have a video that's coming in a few slides, and I would like to.
Okay.
So you have the far field, which is basically RF radiation, as I pointed out. And in this case, it's long range. It's not, you can basically look at a room in a smart home, where you have a TV, you have mobile phones, you have a coffee machine, you have different IoT devices. And you can actually, with RF technology, you can do multicasting. You can do you can power up different devices at the same time. And it's applicable for what we call line of sight or non-line of sight. Okay, so it doesn't have to be a line of sight situation here. And the main limitation is that the efficiency is low. Unlike the inductive coupling, where you have very high efficiency, this efficiency here is low, but we have ways to enhance this efficiency. And also there is some open question regarding safety and health issues when you have microwave in the room. Although that's not really, we have been having now mobile phones for many years, and nothing really came out as a health issue so far. And of course, the application here is extensive. You have sensors, IoT, RFID, and so on. If you would like to compare inductive coupling, and I didn't talk about magnetic, but inductive coupling is very efficient, very strong, but short distance. And it's not multicasting, whereas RF is low, the efficiency is low, but then it's multicasting, and it's basically, lend itself to mobility much more. So, as I said earlier, you have low level, which is basically charging phones, wearable devices, biomedical implants, IoT, and you also have high level, static and dynamic, and that's basically for charging things like EV, electric vehicles, right? And so let's talk about the low level. You have, of course, already know that, for example, you can charge your phone wirelessly, as you can see here in the picture to the right here. And then that's basically a technology that's available to us today. You have a screen, you have a circuit board, and you have the two inductors, like the primary and the secondary. And you have the circuit that basically takes the power from the mains and then use it to do the wireless charging. For the high end or the high level static and dynamic charging, you have the electric vehicle, of course, and the market of EVs is growing so fast, as we know. We have companies like Tesla, for example, and also Ford and GM in the US are looking into EVs very seriously, and as well as companies in China like NIO and other places. And as you see here, 25% of the market share will be autonomous by the year 2035. And the total autonomous vehicle market will be $77 billion US. So, so for wireless power transfer and charging, people are looking into making standards, like, for example, the wireless power transfer 1, which is 3.7 kilowatt, and wireless power transfer 2. These standards will help manufacturers of EV to basically follow the same type of standards when they charge in the charging station. So the way this thing works is that you have a charging station that has these type of technologies transmitting electric field. As you can see here, you have this power converter, you have the transmitter, and then in the car itself, you will have the coil that basically is a resonant receiver, and you have a rectifier and communication between the two, the station and the car, and then you have the battery pack. So we have some examples here to show you, like you have the Qualcomm example of the implementation of this technology, and you have also the solar cell system that's built by Qualcomm as well, solar cell wireless power transfer system. As you can see here, that you have basically, instead of using the grid, you have basically solar cell that harvest the energy and then use it to power up cars that are basically parked for a long time. And we have been working with a company, as I was a research center in Tennessee. I'm going to show you in a few minutes, but before I go there, I just wanted you to look at this picture here, which is kind of a scenario that's actually started to become reality in a few places. So you have actually the power grid, and the power grid basically powers up stations to charge cars that are parked. And you also have a small part of the city that's devoted to dynamic wireless charging. While cars are moving, there's infrastructure that can be built to make sure that, and I'm going to talk about that in the next few slides.
Dear Professor, we cannot see your slides, but...
Can you see it now, or?
No?
Let's see here. Maybe it's just some delay. Is it, can you see it now or not?
No, unfortunately not. I thought you are going to show the slides later, but we cannot see it.
Can you see this one, for example, or when did you lose the slides?
Never. We thought you are just talking and showing the slides later, because I asked you, do you have some videos or slides to
okay.
show?
So maybe I can try to, I don't know if, can you see the slides now, or do you want me to? Let's see.
Oh.
Can you see it now, or?
Yes, I think yes.
So there is some delay, I guess. Okay, let me go to the slideshow. Can you see it now?
Yes, we can see. You can go very fast on the slides, because we could not see them.
You can now see it, right?
Yes.
Okay, very good. So I was just talking about the solar cell wireless power transfer system. As you can see here, that's also a technology that was done by Qualcomm.
Dear sir, which slide number are you talking?
Slide
number 30.
Okay.
Dear Professor Ismail, perhaps you will tell our administrator the slide number so that he can show it.
Okay, very good.
This may be faster.
I will do that. So slide 30. Slide 31, as I pointed out, this is a scenario that it's now emerging in many smart cities in the US and Europe and maybe other places as well, where you have the power grid, the smart grid here, and powering up the stations for static charging, as well as infrastructure, like you have a specific lane here devoted for dynamic electric vehicle charging. I'm going to talk about that in the next few slides. Slide 31 still just shows vehicles can simply return and park to charge by using wireless charging pads, and also vehicles parked for a relatively long time. And you have dynamic charging system, as I pointed out. Slide 32. That actually shows you how the dynamic charging is done. So you have actually an infrastructure. You can see here, like this transmitting coil, okay, which is basically in green here. You have transmitter power electrodes, which is basically these electrodes here, okay, and you have a receiving coil. So while the car is moving, along the infrastructure, that charging takes place. And so you have this type of you have an AC power coming from the mains. It changes to DC, and then the DC there is a circuit that transfers the DC to high frequency AC that feeds the inductance, the primary inductance, and then you have the mutual coupling, and then you'll get a DC. You will convert that DC to AC, and then the AC to DC, and then you go to a battery to charge. Okay, same thing here. This is just an illustrative. So, and now in smart cities, you will have a lane dedicated to this type of dynamic charging, and the average air gap between the two inductors is about 150 to 300 millimeter for small vehicles. It may actually increase for larger vehicles. So the very important thing here is that air gap should not be too large, so that you can make charging more efficient. There is also a technology coming up where you put the coils in the wheel itself. As you can see here, you have, so that would make the air gap very small. Like you can see here in this slide, that you have in the wheel itself, you have the inductance, and then you have the infrastructure.
Dear Professor, you said the inductor is in the wheel, but in the slide there is maybe a different slide. I'm not sure.
I'm in the slide 34 now.
34. So please each time tell the numbers so that our administrator can refresh
Okay.
the slides.
I will do that. So slide 34. You can see now that the wheel will be fitted was inductors, and the infrastructure, you have it here, that would allow you to do like very small air gap, and the misalignment problem would be taken care of this way. So this is actually slide 35, shows you a picture of the Qualcomm infrastructure that was built, and it was actually tested in a place in France with Renault. Okay, that's slide 36. Shows you the demonstration of dynamic charge taking place. They built about 100-meter test track, and it's very interesting. It has been a very successful experiment from what I know. Now I'm going to show you this video. We are actually working very closely with this Oak Ridge. Slide 37 now. If you can upload that video. Let's see here. I have to play it. 37, okay?
Wireless power transfer is an innovative approach using magnetic resonance coupling of air core transformers designed for today's growing plug-in electric vehicle market. This technology can provide a convenient, safe, and flexible means to charge electric vehicles under stationary and dynamic conditions.
But we cannot see the video. Just
plug-in electric vehicles are burdened by the need for cable and plug chargers.
Can you see the video now?
Isolation of the onboard electronics, bulk.
Unfortunately, not.
Is he able to download it from his side? The administrator. Slide 37. Maybe it's a delay a little bit because it's a video stream. Let me try.
You are muted. Dear Oguzhan, you are muted.
I am muted.
No.
Dear
Administrator.
professor, can you stop the sharing and then share your whole screen? Because we are not showing your presentation and videos. Share, click and share screen and then select whole screen.
Okay, I have entire screen here,
Yes.
and now can you see the slide 37?
No. We can. Can you click the share screen?
Can you see now the slide number 37? Yes?
No.
So I'm actually sharing the screen. I didn't do anything different.
Tamam.
So you
Dear
said that
professor, can you see me?
you said that the admin has the slides. He can actually change himself, right?
Yes, but we couldn't see we couldn't see video in your presentation because of this. If you share whole screen
Yeah,
and
I am
show
sharing.
the your presentation,
I didn't touch anything from the beginning. It's exactly the same. So maybe the system basically is delayed or something. I don't know.
maybe
Let me try again here.
we can try share whole screen. Maybe it will be resolved.
Maybe the communication lines are heavily loaded. I don't know. Maybe this
Let
may
me
be the
try
reason.
here. So I'm gonna try again from the beginning. Share.
Please firstly stop share and then share screen and then select whole screen, entire screen. But first,
Entire
stop
screen.
share screen.
Can you see anything now, or because the presentation is uploaded already? I mean, the administrator should have access to it, right?
Yes, but you must share your screen to see presentation, show presentation.
Okay. So let me share again. So when I go to share, I select share screen or slides.
Share screen, please
Share
select.
screen. Okay. So
Yes,
I'm now. I click the share screen.
and whole
Now,
screen.
okay. So I did that.
Entire.
So can you see the screen now, or?
No.
So I'm doing exactly like you tell me.
Firstly, share screen and choose entire screen and
Yeah.
click share.
Okay. Yeah. The share is not somehow it's coming shaded. It's not that system is really I don't know why we didn't use Zoom instead. But yeah. Shows what to share here. Okay. Can you see now anything?
Yes, we
Yes.
can. Your whole screen. We can see your whole screen.
Okay, can you see now the video?
Wireless power transfer is an innovative
Yes.
approach using
Yes.
magnetic resonance coupling of air core.
Okay. Let me try to make it big here.
Wireless power transfer is an innovative
Yes, we
approach
can
using
see
magnetic resonance
screen.
coupling of air core transformers
Voice
designed for
video.
today's growing plug-in electric vehicle market. This technology can provide a convenient, safe, and flexible means to charge electric vehicles under stationary and dynamic conditions. Plug-in electric vehicles are burdened by the need for cable and plug chargers, galvanic isolation of the onboard electronics, bulk and cost of this charger, and the large energy storage system packs needed. With a system where you have to physically plug in, there are a number of occasions where the owner could very well forget to charge the vehicle. For stationary applications, like charging of plug-in electric vehicles at home, Oak Ridge National Laboratory's innovative wireless power transfer technology adds a convenience factor compared to actually plugging in, which means the vehicle will have a full charge every morning. Electric vehicle charging must be safe, compact, and efficient in order to be convenient for customers. By reconfiguring the transformer and altering the resonance frequency, energy is transferred to the battery with lower energy losses and with fewer demands on the primary circuit by the rest of the transformer system. The Oak Ridge National Laboratory discovery shows that sufficient power for the battery can be transferred from the primary to secondary circuits without significant energy losses if the operating frequency is set between 50 and 95% of the resonance frequency of the circuit. The electrical power is then transmitted to the chargeable battery, which is electrically coupled to the secondary circuit through the air core transformer. Some advantages include reduced energy losses during transfer of energy to the battery, a charge potential that is relatively unaffected by up to 25% misalignment of vehicle. Other receiving components draw less power from the primary circuit. These advantages allow wireless power technology applications to expand at the workplace and beyond as the demand for electric vehicles rises. For vehicles that operate over a fixed route, such as buses and shuttle vehicles, wireless power transfer means that a smaller battery pack can be used. In the traditional system, the battery pack is designed to accommodate the needs of the entire route or shift. With wireless power transfer, the battery can be downsized because it can be charged when the vehicle stops on its route. A rental car shuttle bus, for example, can charge when it waits in the terminal and again when it waits at the rental car place. Thus, the battery only needs enough charge to get to the next stop. This decrease in battery size means significant cost savings to electrify the vehicle. This technology enables efficient opportunity charging stations for predefined routes and planned stops, reducing downtime. Charging can occur in minutes. This improvement also eliminates the harmful emissions that occur in garages while buses are idling during charging. In larger cities, dynamic charging offers an even greater impact utilizing existing infrastructure. As vehicles travel along busy freeways and interstate systems, wireless charging can occur while the vehicle is in motion. With this technology, a vehicle essentially has unlimited electric range while using a relatively small battery pack. In-motion charging stations use vehicle sensors to alert the driver. Traveling at normal speeds, sensors establish in-motion charging. Wireless power transfer transmit pads sequentially energize to the negotiated power level based on vehicle speed and its requested charging energy. Lower power when vehicle speed is slow, and much higher power for faster-moving vehicles. Dynamic charging would allow electricity to supply a very large fraction of the energy for the transportation sector and reduce greatly petroleum consumption. Previously worrisome traffic delays now provide longer periods of charge while passing over in-motion chargers. Inclement weather such as rain and snow do not affect the charging capability. At Oak Ridge National Laboratory, we are working to develop the robust nature of wireless power technology to provide a convenient, safe, and flexible means to charge electric vehicles under stationary and dynamic conditions.
Okay, so we go to slide 38. Can you hear me? Hello,
Yes.
can you hear me?
Please, slide 38, please.
Okay. So, the as I said earlier, we had these different types of wireless charging, and one of them, of course, is RF radiation, which we just show. We will see in the next few slides. So we have, of course, like now we're done with the EVs, electric vehicles. Now we show how can we charge all these IoT devices, like that are basically coming in large numbers. Consumer electronics, wearable and medical electronics. Many of those devices would love to be able to benefit from this technology and basically avoid using batteries, for a better environment, okay? And of course, circuit efficiency plays a major role in battery lifetime. So if the circuit is efficient, it does not consume too much, and the battery would live longer. But okay, so what are the scenarios that the people are looking at for wireless power transfer technology? So we have the solar power satellite. So you have actually a satellite that's fitted with solar and basically takes the energy from the sun and then transfer that energy to the earth, as you can see here, that can be used actually for charging, like, microwave receiving antenna situated on earth, microwave receiver antenna convert microwave signals into electricity, okay? So this is one scenario. And this electricity, of course, can be used to power home, office, different parts of the city. Other scenario, of course, is in a smart home. As you can see here, you can actually use RF wireless power technology to power up different devices, as you can see here. Appliances and small gadgets, mobile phones, laptops, and so on. Another scenario, which is very interesting, also in a city. So you will have, you don't have to actually stop the car and charge the vehicle. You can actually fit the city with power beam transmitters installed on the highways in busy traffic areas. Power sources convert electricity into power beams. This is slide number, let's see what the number is here. 42, slide number 42. Okay. Now we also have another project which I spoke about in the beginning of the presentation, which how can we use wireless power transfer technology to basically enhance the efficiency and charge a device anywhere it exists, basically it's the same way, like I said, in a Wi-Fi situation. So you have a transmitting antenna. We are going to be using antenna arrays and then use the wireless power transfer technology for a receiving antenna, following by matching network, rectifier, and then the DC to charge the battery, a load, basically. So, and we use basically, in order to enhance the efficiency, we use reflecting walls. So we basically put, like you can see here, a system that we experimented with. If you have, like, say, 10 antennas, transmitting antennas, as you can see here, located in the Z axis, like Z direction, and you have a receiving antenna that's also directed in the Z oriented, it's a dipole antenna, Then the first scenario is that the receiver here will send a pilot signal. As you can see, the receiver here will send a pilot signal to identify itself, okay? And then okay, I don't know why it's not, yeah, here it is. The through channel reciprocity, we are now on slide 45. We have a technology called time reversal, or, some of you who are familiar with microwave, through channel reciprocity, the transmit will send a phase conjugated version of the signal to refocus the signal at the receiver. Okay, so first, just to explain more, the receiver will send a pilot signal to identify itself. Then the transmitter will send the main beam here, and then you have side lobes, as you can see here. And then these things will basically get reflected, as you can see, from different walls around, and hopefully it will come back to the receiver in a spatial temporal focusing effect. So as long as the target receiver broadcast pilot signal, the wireless power beams would follow their motion dynamically. Okay, so it would allow the charging and the power up of multiple devices. It's not only one device that can be charged this way, but you can have several devices in the room being charged with high efficiency. Slide 46. So the amplitude and the phase variation, you can see in this picture here that you will have the receiver right here, and you have the antenna array here, and you have reflecting walls. So these antenna arrays will basically result in a beam, the main beam, and you have the side lobes here. Same thing from these antenna arrays. And these side lobes will actually result in several multipath signals that can actually combine in a constructive way and give the receiver a very strong, efficient signal that the receiver can harvest and uses to do charging. Okay, so this is basically the what's happening here. So this type of scenario in the left will lead to a very interesting scenario to the right. You have a focused maximum power at the receiver. This is the receiver right here. Then you have multiple hotspots with different power density. So as you can see, different colors here, like green and red. And this is the power density level. In some cases, you might have these signals coming in a destructive way. And that's when you have what we call dark spots or cold spots in blue here. Let me just find here, this one. So that actually looks like very much like what ubiquitous, similar to what we have in Wi-Fi, where you actually have a room that has different strength at different location of the room. So here you have actually, you turn this room into a wireless charging environment where you can have different devices located in different areas that can receive this energy, and then use that energy to harvest and convert it to DC power. So that we can actually even enhance this efficiency by using what we call meta surfaces here. So we are now on the next slide, which is 47, I think 48, I would say. So so if you look at these two images here, this is basically free space. There is no reflecting walls. You only have one receiver. You don't have any. You have to be in this area here to get any. You have to be here. You can see my cursor here. But with reflecting walls, you will have several hotspots with different strengths, as you can see here. So in the presence of reflecting walls, you have multiple and additional hotspots in indoor environment were created. So you have a multipath environment. Almost we have a total space coverage with different power levels. And like I said here, it basically makes possible, the next slide, 49, makes possible for electric power to become as ubiquitous as Wi-Fi. So charging and or powering up sensors, IoTs, and you can also, this approach can be used in many applications, ranging from charging of small devices to charging like electric vehicles and other places, as you can see here. And finally, in this slide, slide 49, we have, we can enhance this by using what we call meta surfaces here. The meta surface can in fact make the efficiency much higher. So you can have a feedback mechanism where the meta surfaces adjust their phases depending on the collected power by the receiver. Okay, and that's actually a pattern that we have it bending, and we are experimenting it right now with this type of technology in the lab in Twain State. So in conclusion, we have slide 50, We have a review of current wireless charging technologies. We introduced the basics of a disruptive wireless charging technology for static and dynamic charging. We presented the technology that takes advantage of phased array waves, allowing efficient and enhanced harvesting of RF signals. And this leads to what we call seamless wireless charging environment, which we just described. And the technology that we proposed would lend itself to a variety of applications, ranging from EVs to IoT and smart homes and wearable devices. Here. Okay, thank you so much. And I really appreciate your invitation. And I hope that you find this presentation useful. Any questions or any comments? Can you hear me?
Thank you very much for this enjoyable and interesting talk. So, any questions from the audience? I see there are no questions. Maybe I can ask one question. What will be the next step in this area? What do you think in your research and for future? What do you expect?
Yeah, actually, right now we are actually let's see here. This one, we are experimenting with this one right now, and we are trying to basically either license this technology to some companies in the area of Detroit, which is like we're talking to a couple of companies. I cannot reveal the names, to see if they can license this. They are very excited about this technology and they would like to license it and use it in their products, basically. So that's what we're looking at right now.
Okay. Thank you very much again for this interesting talk. So I think we can close this invited talk session now. Many thanks to you
Sure.
joining us in this session. And the last sessions of ELECO 2021 has just started. Thank you for joining us, everybody. See you in the next conferences, this time in person, hopefully.
Yeah, I hope so. Thank you so much. Greetings to all. Bye-bye. Bye-bye.
We would like to thank Professor Mr. Ismail for the eye-opening and valuable information he gave in the presentation. And also thank you for his explanatory answers and efforts. It was a really beneficial presentation, which was to contain recent and attractive topic around the world nowadays for everyone. And thanks to dear Professor Oguzhan Cicekoglu for his contributions and helps. Now, with your permission, I would like to thank everyone who contributed during the conference. During the ELECO 2021, 7 distinguished invited speakers from the world of science made their presentation in our live broadcast. We would like to thank all our dear invited speakers from various countries of the world who joined us despite the time difference for valuable information that makes us love science again they provided. We would like to thank all our dear season chairs who dedicated precious time to us for management and contributions. We would also like to thank the participants who presented their precious studies to us and our valuable listeners. We would like to thank Chairman of the Chamber of Electrical Engineers, Bursa Branch, Mr. Mehmetcan, and EMO employees for their contribution to the conference. I would like to thank Emin Sezener, who took part in our technical team, who contributed a lot in the realization of this live broadcast and Zoom seasons, and my dear friend Zeynep Özerol, with whom I shared the task of presenting this conference. I hope we can meet next year at the conference face to face and without fear of COVID-19. Thank you for your understanding in all the problems we experienced during the live broadcast and Zoom seasons. Our conference will continue with the Zoom seasons, and this is how we will end the day and conference. For season linked and detailed conference program, please visit www.eleco.org.tr. I hope science continues to illuminate your path. See you for now. Have a healthy and good day.
I am Bursa. I am a World Heritage Site from the depths of history. I am a depository of civilizations on the foothills of Mount Uludağ. I am the ancient capital of the Ottoman Empire and its enduring spirit. I am Bursa. I am the prayers and calligraphy of the Ulu Mosque. I am the tiles and ceramics that give the Green Mosque its name. I am the houses of worship in Iznik, once home to Romans, Byzantines, Seljuks, and Ottomans. I am the Muradiya Mosque complex, where life and death, dreams and reality, poignance and joy are contemplated. I am a boundless land of legends, the living cultural heritage of Cumalicuzic, the sun setting on Gölyaza Lake. I am nature's gift to humanity. I am the color green in all its shades. I, a centuries-old sycamore, tones of blue and green, sun and lake, am Bursa. I am the eternal beauty of the Longos forest. I am the rushing waters of the Sai Tabat and Suuchtu Falls. I am a city of flavors, where history meets gastronomy. I am crispy jontic from a wood-fired oven. I am the finest olives and olive oil. I am the birthplace of Bursa kebab. I am köfte with pide and inegöl köfte, that is, a paradise of Turkish-style meatballs. I delight palates with sensational flavors, like soft tahini pide and candied chestnuts. I am a land of fresh fruit and nature's bounty. I am paragliding between sky and forest. I am the center for adrenaline and nature sports. I am the timeless shadow puppets, karagöz and hajavat. I am handicrafts at Erganda Bridge, a steel knife forged in fire, a smooth silk shawl from Kozahan, a handcrafted Iznik tile. I am the last stop before Europe on the Silk Road, the covered bazaar. I am so much more than a city. I am Bursa.